All right, I just wanted to make one more quick video with some little notes that might be helpful to you. So if you've watched the other ones, or you have a good idea, hopefully, of how these solids are constructed, what they look like. I showed with my Desmos tool kind of what they look like as you rotate around and the solid and stuff to see it from some different angles. But when it comes down to it, when you're writing let me go back to the main screen here. When you're writing the volume setups for these solids, it is very formulaic. Anytime that you are making one of these solids with a certain shape perpendicular to the x-axis, which I did every other time here, that means the solid is going vertically, perpendicular to the x-axis, that cross-section. The things that you're going to have x values for the limits of integration. So the way we defined them, that was from A to B. Those were x values. And I actually, on my paper, I would write down A to B, because in my work before then, I would define A and B as the intersections of f and g, or whatever the functions are, right? So if you define them that way, then you can just use A and B. Not only that, I used A and B in my calculator because I stored those intersection x values as A and B. So it makes it easier for you too not to make a mistake as to which thing to use. You show the work of getting the intersections, you store them as A and B in your calculator, you write down A and B, the values on your calculator, on your paper as well, while calling them A and B. And then in your work, in your setups, you can just call them A and B every step along the way. Another thing, besides the limits of integration, you have dx, right? It's with respect to x because that vertical cross-section has its width. The width of those little rectangles is a tiny width on the x-axis. So it's a change in x. So these are dx. And then the functions in here are in terms of x. Okay, now you can change the variable. You don't have to keep it with x. You could use smiley face as a variable if you really wanted to. It's pretty non-standard, but you could. But I kept it consistent here to match the graph. So on paper, on this screen, my x's are x's and my y's are y's. When I did it in the calculator, I used x for everything. I didn't use the y's. But on paper, I think it makes it nice and clear to keep it with those variables. So vertical cross sections, again, perpendicular to x-axis, x values for limits, functions of x in the integral, and dx for the differential. When the cross sections are horizontal, when you're perpendicular to the y-axis, like on these, now you have y values for the limits of integration. You have dy for your differential, and you have functions of y inside the integral, okay? And again, you can change the variable there if you want to. Like in the calculator, we used x, but it should be those functions that came from y values when you do it. So that's what you have to keep track of. And another thing to watch too, we had to be careful with this. When we were going vertically, f was on top. It had the bigger y value going vertically. So when I want that length of that rectangle, that height of it, right, then I want f minus g, because f is bigger than g, so I want to subtract and get a positive answer. But when I'm going horizontally, now I'm looking at x values. G is on the right of f. So g has the bigger x value than f. And so now I'm doing the g curve minus the f curve, which is why all of these that were going horizontally have g inverse minus f inverse, while all of them that are going vertically have f minus g. So that stuff is itemized right here. When you have vertical cross sections, we're perpendicular to the x-axis. You're going to have x values for limits of integration. You're going to have dx for your differential. And your integrand is going to be in terms of x, y as a function of x inside. So we used f of x minus g of x on all those problems. When you have horizontal cross sections, because it's perpendicular to the y-axis, when that happens, you're going to have y values for your limits of integration. So we used c and d. You're going to have, dy for the differential. Oops, it's an oopsies there. And here, let me fix that with this stuff out of the way. Dy for the differential. And you're going to have x as a function of y inside. So you're going to have inverses of f and g is what we used, right? You're going to have the inside, the integrand will have y's in it, not x's then, to match that dy for the differential. Okay? The other piece of this that I have in these notes here are just the coefficients for each shape. And the only ones that I've seen on the AP exam, and I've looked at a lot of AP exams, are squares, semicircles, right isosceles triangles with a hypotenuse in the region, right isosceles triangles with a leg in the region, and equilateral triangles, and rectangles with a height that maybe is defined as a multiple of the base or something like that. Those are the only ones where you had to like figure out your own area function. Now, could they put regular hexagons on there? They could. I really doubt they would, but they could. I've thrown it at my classes before just for fun. Regular hexagons would be pretty easy though. It's not that big of a deal because if you draw a regular hexagon, my point in doing this isn't because I think you might see regular hexagons on the AP exam. It's just to point out it could be any shape. As long as we can find the area of that shape in terms of one dimension of it, one side length of it, then we can do it. We can integrate it. If you take a regular hexagon and you do all of the bigger diagonals going across, you create 1, 2, 3, 4, 5, 6 equilateral triangles. And each one of those equilateral triangles is the same as this equilateral triangle. So the area of a regular hexagon with side length s is exactly 6 times the area of an equilateral triangle with side length s. And so this coefficient is just this coefficient times 6. Again, I'd be very surprised if we saw that on an AP exam. But that's the big idea here. If you can get the coefficient for the shape based on how much of the square it fills up. And I talked about this in the last video, the triangles one. For example, again, just to really quickly show, if I draw a square, this coefficient here for semicircles, what it means is that if I put a semicircle there in the square where the diameter is the same as the side length of the square, that semicircle fills up pi over 8 of the square. If I put a right isosceles triangle with a hypotenuse as a side length in S, so where the side length of the square is going, that isosceles triangle, isosceles right triangle, fills up 1/4 of the square's area. This triangle fills up 1/2 of the square's area. This triangle fills up radical 3/4 of the square's area. This rectangle is k times as big of an area as the square, and this regular hexagon is 3 radical 3/2 times as big as the area of that square. That's what those coefficients mean, and once you understand what they look like and how to apply them, it makes it so easy to do these solids. So I hope this was helpful. Good luck.